All right. In the in the last lecture, on the last video, I mean the first video that we had. Um, hope everyone was there in the meeting. We talked about temperature conversions and also just temperature conversion. So this covers. In fact, it's not is ICH, which is industrial chemist 270. This is supposed to be 370. Then also just the CH270. All right. For industrial chemist guys, they are doing it at what? 370 level. Okay. So just the same, just know that it's 270 as it stand. Okay. According to the CBU standard, um, we have talked about a bit of intro of thermodynamics, and we saw some changes that were taking place and also what we'll be doing. We also talk about even integration in this. So this physical chemist combines chemistry itself, where reaction will be taking a bit of physics, where we need conversions of units and everything like that, and also mathematics itself will have a bit of mathematics inside. So it will be actually an interesting course. So we'll be enjoying it together. So now what will happen is we'll talk about now partial and complete derivatives of some formulas. All right. So that is it about this. Okay. All right. So now suppose you are given a function to say y, all right, is equal to just let's say x, like that. So now to find the derivative, all right, so we'll talk about complete and partial derivatives. All right. So to find the derivative of this function, all right, so this function you can see that it's depending on what? On on x. The y function depending on what? X. So we can say this is a function. A function is just a rule that relates two or more variables. All right. And the inside thing that actually, so this one is what? Dependent. Then this one is what? Independence or independent. So this one doesn't depend on any, but this one depend on the. So once the value of this one increases, then the value of this one also increases. But at this point they are equal. So we can have a point whereby we have y, let's say, is equals to 2x. So when x reduces, then this we expect something in this. Again, when x, let's say, increases, all right, we also expect something in what? Increase in y. So we are saying now a function is just a relationship, and a function is just actually the rule that relates two or more variables, and these variables, they actually contain what we call an operator. So an operator, suppose you have y is equal to let's say 3x squared. So an operator is this point, all right, or let me say again, y is equal to 3x. All right. So an operator is this one, which will be causing some changes. So an operator is just an entity operating on a certain function. So it will be operating in this function, okay, so that it can generate a new function itself. Suppose I change in x there, it will still have a what? A function. Or again, the same operator, this we have operator here. Once it changes, it can bring what we call now a constant entity. Let's say we derive this, it will be 3. This one, when you derive this, it will be what? 3x or just 6x, something like that. So by this is a function. Again, this is what? A constant entity. So that's what we mean when we say a function, and also just an operator. An operator is just actually um, an entity operating on a certain function to generate a new function or just a constant entity. Then a function is something that relates two or more what? Variables. So hope that is clear. So we did all those things in class. So from there, then what we are going to do is um we are talking about derivatives. So you have complete and partial derivatives. So since you never, what's this? You didn't do partial derivatives, some of you. So now we'll be there to actually explain what that means. So when you say something is partial, it means something is changing then the other one is kept what? Constant. It's more like when it is partial, something can't change completely. It will be just changing on just a bit of it, all right, not completely. So suppose I give you to say um we have, let's say, a function z. So this function z, we are saying a function, all right, so it depends on x and what? And y, all right. So it depends on these two guys, all right. Suppose this is a volume, then this is pressure, and this is work. So work will be depending on these two things, all right. So get a clear picture now. So if I say, can you find the complete derivative? So a complete derivative now, by the way, the process of deriving something or just finding the dy dx of a something, you are trying to reduce, and by that you are trying to find the gradient. A gradient now reaching at the point whereby you want to see the slope. All right. So for me to say a complete derivative, I'll do every partial of it. So I'll touch this derivative and also touch this derivative. That's what to bring about what? Complete derivative. So suppose now we are told, can you find the complete derivative of this function that depend on x and y? What I'm going to do is um I'll say dz, all right? So dz is changing in x and y. So I'll just say dz, all right? So this dz will be changing, all right? So I'll light the partial. It will be changing on the partial or on the side of x. That's what we call now a partial because it's not changing on both. So I'll say, so partial of z, all right? So partial of z, it can change at what? In the partial of what? X, all right? So by this, if I do this, then I'm in the change of partial of x. Down there is what changes, all right? Hope that is clear. Down here is what? Suppose I give you, let's say, 3x. Okay, y is equals to 3x, all right? So we can see that what changes if I find dy is this function, right? I put y after d. That's the reason why I've put dz there. So by that, I'm saying dy is equal to what? There will be 3, right? What changes? So dx, the one what you put down there, the d something is what changes, and the x will change into 1, right? So that will be just 3, which is a constant entity. So if I put dx, meaning that the x is the one changing partial. This is the partial derivative. That symbol is called partial derivative. All right. Okay. So this is the partial derivative in what? In x. Then I'll keep constant y. All right. Then we know that this will be what? Relating to dx. All right. So it's just this one, just maintain what? The partial thing. Don't get confused. So that's how we start. All right. Then plus again, I'll say again the partial derivative of the same z, but in this case, we'll get the partial change in what? Change in y. All right. Then from there, then I'll keep constant what? X. I'll hold x. Then I'm interested in the dy. So this is what we call a complete derivative of a what? Of a function. All right. This is the partial, right? And also this is a partial. All right. So both they are making what we call um complete. All right. Hope that is clear. So now that we have known this concept, let's go and do something. What you are going to do is, suppose now you are given a function to say, uh, um, let me just lab this. Hope that is clear. Or let me just go to the next page. Okay. Suppose now you are given the function to say, g depend on the function what? On the variables t and what? Pressure. All right, temperature and pressure. So now to find the complete derivative of g, we'll say dg, all right, will have the change, a bit of change in temperature, or yeah, let me start with a bit of temperature. So I'm saying this partial in g, all right, there will be a partial change in what? In a bit of t, all right. By that, I'll maintain p. I'll hold p because I'm just changing. So when this one is changing, we'll also put what? dx there, which is the dx, because it's changing in x. All right. Then from there, all right, um so this dx is coming as a result. Suppose I give you a function u is equals to what? X. Then I'll say du, all right, there will be change in x. So I'll say dx is equal to this one. When you differentiate this one to give you what? To give you what? It will give you 1. So I'll say du, all right, is equal to, you multiply throughout, that will be dx just. Okay. That's the reason why we are putting this change, to show that it has changed what? This thing inside the bracket is as a result of change, and that will be abbreviated by this x to mean it changed in x. Hope that is clear. And what you are going to do is, we'll say, hope that is clear. Don't get confused. You are still doing a lot of things, and it will be important that you understand that now. Then what you're going to do is, let me lab this. So we can see that we have changed a bit of t plus, again, let's change the partial derivative of g. All right, it's now a change in what? Change in what? In pressure. Then this change in pressure will hold what? Temperature, because we have already differentiated temperature, and will write the what? dp like that. So this is the complete derivative of this function. Hope that is clear. All right. So the function was depending on these two, and this is the complete derivative. And we'll see how we can also find just the partial derivative. Well, let's say you are told to find this part. All right. We'll see how we can do that. Just know that when you are given such a part, you are only interested in that part, and you don't bring the other. So that is it. So now suppose you are given a function again. I just want to train you on how we were doing these things in case you never understand this. So it's important that you understand them right now. Okay. Suppose I give you the function again. They say the same function g depends on what? On these three things. So we have t, p, n1, and also let's say n2. All right. So now we are saying the complete derivative of g. All right, the complete derivative of g will be as follow. We'll say dg. All right. Okay, I'll be done soon. Okay, or you can just see it. Okay, so now the g will be as follow. All right, there will be a partial derivative in what? In the same g. All right, but in this case I'll differentiate what? T. So I'll say partial in the t. All right, then I'll maintain p. All right, n more 1, then again more 2. All right, so I'll maintain this, I'll hold this constant. So I'll say this will present what? Change in temperature dt. Then from there, here again there will be a partial derivative in g. Now maintaining what? I'll now get a bit of partial in p. All right, then this will show to say there was change in what? In p. Then we'll hold t, n1, n2 constant. All right, then plus again. All right, so again there will be a partial change in g. All right, now we are changing what? We get a bit change in what? In n1. Then this will show to say this is the change in what? N1. All right, then we hold constant t. All right, p and n2. Then plus again there will be change, a bit of change in g, now with reference to what? dn2. All right, then this will be what? Now we'll keep temperature, we'll hold temperature, and also what? N1 like that. Then this is what? dn2 like that, to show that there was change in what? N. So that's the complete derivative of the function g. Hope that is clear. All right, hope that is clear. So that's how you'll be finding that. Okay. Suppose now we have the function again. So let me just go back in case you are confused. Let me just go back. So I want to show you how we'll be finding a bit of it to extract a bit in it. So suppose we have this function, right? And I tell you to say, can you find the derivative of this one? You say dy, all right? The same function. Now you write what changes dx, all right? So this one will multiply the coefficient there. So that will be n, all right? X, then n minus 1, right? That's what we'll be doing there. Okay. So in short, this y, we know that dy and y is equals to this, right? Y is equal to this. All right. Okay. So y is equal to that. So we'll replace x the power n like that, all right? Then over dx. Okay. So meaning that there was just a bit of change in this one, and that's what we'll be bringing about what partial derivative. So we'll be lighting this. We light this inside. We are only interested with what we put down. All right. So that is it. So if I give you to say y is equals to x, what will be the dy dx of this one? So you put x there, all right? Then dx down there. And when you divide this, will give you what? 1. That's the reason why dx dy is equal to what? 1, like that. Okay. Let me now start the work by saying, suppose now I give you the derivative of now these gas equations, and let me talk about one of the common gas equation we know, and that's what we call ideal gas equation. All right, and let's say I give you a reference to say it has what? 1 mole. All right, so what I'm going to do is I'll say this is the ideal gas PV, all right, is equal to what? nRT, like that. Okay. So from there, I'll put now pressure as the subject of the formula. So I'll write pressure is equal to what? nR what? T over V, like that. Okay. So now we can see that pressure now in this case will be depending on what? Volume, and also R, though R is a what? A gas constant, and the temperature will be changing a bit. Now I'll give you to say 1 more. So I've given you the difference, meaning that is a constant number. And in differentiation, we are not considering what? The constant number. So what you're going to do is the complete derivative now. So this guy now, P will be what? Will be changing, or will be depending on the what? On the temperature and what? Volume, like that. Okay. So now complete derivative of P, it will be dP is equal to a bit of change in what? A bit of change in what? In the same P, all right, over now we are changing temperature. So I'll change a bit of temperature, all right. Then we'll say, um, I'll say I'll hold now volume there, all right. I'll say dt, okay. Plus, again, I'll get my a bit of change in pressure, all right, now with a reference to what? Change in volume, all right. This represents change in volume dv. Then I'll hold what? Temperature, like that. So this is the complete derivative of the gas, all right. Right. So then again, we can find this, everything like that, change in temperature, partial, everything like that. So far that's how we'll be finding this. All right, hope that is clear. All right, hope that is clear. Then again, if what if I tell you to say, can you find, all right, can you find in the same gas equation which we left at the point of um RT? I said that more, the end that we had, it was just disturbing. Like I've given the reference to say it's 1, so there's no need of you lighting it. All right, you can even light it, but it doesn't make sense. All right, I've given you the reference to say remove that. Okay. Okay, that is it. So now we are told to say, can you find the dv in this point? All right. So if we are to find the dv now, what you are going to do is you make v the subject of the formula, right? So v will be now r t, all right, over what? pressure. And this is a gas constant, right? So we can differentiate a constant. So say V is equals to what? T over what? P. All right. So I can even write as inverse, but I'll just leave at this point. So meaning that V will be depending as a function of what? T and the pressure, like that. Okay. So now dV will be we have a partial derivative of the same V over what? Change in what? Temperature. So a bit of change in temperature, then we'll keep P constant, then this to show there was change in what? In temperature. So I'll say dt. Plus, again, a bit of change in volume over, all right, now we have a bit change of what? Pressure. Then this means dp, change in pressure, then we'll keep what? Volume there. So that's the formula we'll be using. I mean, that's the the dv. We can also have the dt and try to find dt. All right, try to find dt. Okay, so from there, then let's do the exercise that we were given in class. All right, so the exercise that we were given in class, we were given this gas equation, Van der Waals gas equation, which actually gives us P, all right, P, all right, okay, open bracket, V minus B, like that, all right, is equal to what? R T, like that. Okay, so then we are told to say find, all right, find one partial derivative in P, okay, change in what? In temperature. All right, then holding what? V constant. Okay, so how are we going to find this? This was an exercise which we were given as a homework. So what you're going to do is, so we can see P here is what? Is the one on top, meaning it's the subject of the formula. So what you do is you write P is equal to what? RT, all right, over V minus B. All right, so you can see now that you can now see that um you can now see that um you can now see that R itself, uh P will be depending on this one, but R is a constant. I've not mentioned about it, but I just want you to include. So we are now finding this. So meaning that there will be just a change in what? In temperature. All right. So wherever there's temperature, there will be change. So what you do is you say to find this partial derivative in P is already the subject of the formula there. So to find the derivative, we'll say the partial derivative in T, change in T, all right, holding what? V constant, like that. So what you are going to do is this will be equal to what? You bring the same thing there, the partial of everything that you have there, all right? So the partial of everything that we have, which is P, and the P, this point is what? Is equal to this. All right. Hope that is clear. So I'll put P wherever there is what? This P here, which is here, I'll put that. So I'll put R T, all right, over volume, all right, minus B, like that. Okay, that's my P, right? Then there will be what? Over, this was supposed to be over the partial in what? T, all right, right? Then you do this for a partial thing, then you do what? You maintain that one which they gave you, like that. So what you do is you can distribute throughout inside, you can see there, all right. So that will be now partial in T, then I'll have R there, all right, over partial in T, all right, then this will be what? V, because I'm not interested in V what and that, because they what? They are not having T. The change is only based on T. So this and this we can see they can do cancel. So have R over what? V minus B, like this. So that's how we are supposed to find this homework question. All right. Hope that is clear. So that is it. Suppose we have again the gas equation to say suppose we have the gas equation, all right. Suppose you have the gas equation to say, no, let me not write this gas equation. I'll write this gas equation to say P, all right, plus Q over V squared, then open bracket V minus B like that, okay, then is equal to RT like that. So now we are told to find, let's say, find dp. All right, so how are we going to find this dp we have here? And let's say the information is that a, all right, b, all right, and the r, all right, they are constant. Okay, so this is a, by the way. Okay, so that's a, and also r, they are constant, so meaning that we won't be actually interested in those. So we'll actually do this. We'll say, since I'll take this one to the other side, or I can just cancel whenever there's this. All right. So I'll say P, all right. First of all, divide this minus B, all right. This goes, then we'll have B minus B like that. Okay. Then this one to go to the other side. So it will be pressure, all right. Pressure is equal to RT, all right. Then V minus B. Then this one will come this side. That will be now A over V squared. All right. So we can see that this one is constant, this one is constant, this one is constant. So we can see that this pressure will be only depending on what? On the temperature and also the volume. Those are the two things that we have, right? So to find now the dp itself, so the derivative of pressure now will be what? There will be change in T and also change in what? V. We have done this. So you go and try find me what? dp. But this function relies on temperature and also volume. So you can find the complete. So when you just write like this is the complete derivative. So you go try that. Okay. So let's talk about something else. Let's talk about something important now. All right. So suppose the same gas equation now, all right? Suppose I give you to say um, the same gas equation that we have on top there. I mean this one. Let me just light it. Pressure is equal to R T over V minus B, then minus A over V squared. So having this formula now, what you are going to do is, let's say I tell you to say find partial change in P, then with a reference what? To change in V. All right, so that is it. So we want to, then we'll keep temperature constant like that. Okay, so what are we going to do in this case now? I don't tell you any information about this constant. I just want you to include them. So what you are going to do is um we're going to say we'll find, all right, the partial change in temperature and also the partial change in what? In 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 volume as well. All right, how do we achieve that? Okay, so we are interested in the change of volume, right? So what you're going to do is, I'll say partial change in pressure, all right, the way the formula is, I mean the question is, then we'll hold what? Temperature constant. So we won't have any change in temperature, so temperature will be included. So these are partial changes, all right. So I'm interested in the what? Change in V. So take note of this, we are only interested in the change in V. So we have two things here, we have this side and this side. So what I'm going to do is, you say since P is equals to everything here, so I'll say partial change in what? In I'll just let them separate. Partial change in that function P, I was supposed to write the P, but I will present P whatever I have there. So I'll say change now in what? In V. All right. Then open bracket, I'll put R T over v minus b, all right, then minus a over v squared, like that. Okay, so what I'm going to do is I'll distribute this everywhere. So what I'm going to say, I'll say partial change in what, r t, all right, then partial change in what, volume, minus, all right. So here there was what, since there was partial change in volume, then there will be what, v minus b, like that. Then here again we have partial change in E, we don't know, but we write a, then over, so this a is over what, v squared, then we have partial change in what, in volume. We are only interested in the volume change. So what you are going to do is what you are going to do is, all right, so what you are going to do is, we say here we are only interested in change in volume, right? Okay, change in volume and change in volume. So at this point, in fact, here I can't do anything. I'm supposed to lie to say change, all right, in temperature. So I'll put temperature there. Then I have R, all right, then V minus, so volume is changing. What I'm going to do here is, in fact, I'm supposed to rewrite this equation as follows. Before I even do anything, we'll use some rules here that we know in mathematics, such as chain rule, everything like that, to derive this equation. I mean, to differentiate. So what I'm going to say, partial, all right, partial in V, all right. Then what I'm going to have here is R, all right, T, okay. This one will come top there, it will be V minus B, all right, -1 minus, all right, that will be A, all right, V to the power what, -2, like that. So there will be just change in V. We are only interested change in V in this case. So change in V here, what will change something there, and we use product so that this power will come in then to give us what, negative. These are, we won't touch them because they are not our area of interest. Then what we are going to have is negative, the same RT, all right. Then differentiating this one is still be the same. Then here, since we have only one volume, it will give us 1 after applying chain rule. So that will be just V minus B, then we have -2 there, then minus, all right, then change here to be plus, then there it will be 2, all right, then A, then V to be what, -3, like that. Okay, so this is the derivative that we have, and it's just a matter of arranging it. All right, so we have negative R T, like that, over, all right, so this will be now V B, I can write it like this, then 2, then plus, we have 2, right, then over, that is 2A now, then the V now will be like this. Hope that is clear. Hope that is clear. All right, so after you finding dp, then you can go and replace this partial change in it. And we can also find, you try finding what change in partial pressure, and also with reference to change in T now in this case. You try to find that, and you see it will be actually useful. It will come out, but you have already done this, but you would go and try. All right, so that is it. So suppose again I give you these mathematical derivatives. um Suppose I give you to say dz, or just I give you the function y, z is equals to x squared y, all right. Then I tell you to say, can you find dz? So meaning that it's a complete derivative. So what you do is there will be change in x and it's also change in y. So what you do is just write the formula because you don't have the variable. So you say change of z, all right, partial derivative with change of what, with reference to change in what, in x. So I'll say partial change in z, then with reference to what, partial change in x, then all right, then holding what, y constant, like that. then change in dx, which is x. Then again, I'll say partial change in z over partial change in what? In y. Then we'll hold what? X. Then there will be what? Change in dy. So this is a change complete. All right, this is a complete derivative to say. Then we can also write something like, let's say I tell you to say, can you find the partial derivative we change with the an inference to change in what? In x. So I'll say x like that. All right, how do you achieve this? Then you should maintain y constant. What is this? So what you're going to do is change z, we know there, but they'll be changing what? In x only. So what you're going to do is they'll be only change in x, and we know z is that. So I'll say partial change, all right, in what? In z is equal to what? X squared y over, all right, there will be what? Partial change in what? X like that. All right, so what we do is we say, we can see here x and x will cancel. So I'll say partial change in x squared over partial change in x in y. All right, so what I'm going to do is we can differentiate now this one, the x squared over dx. That will be, in short, you are differentiating x squared, and that will give us what? 2x. You can see the x will cancel. All right, then y. So this is the answer that we are supposed to write. So these are mathematical differentiations that we need to be aware of. All right, what if again I tell you to say find now dz? All right, just dz dx. All right, this one you just go direct, and what? This wasn't a partial thing. All right, so this is now exact the same thing, and we are, I was just trying to show you that say change in the x is same as partial change in x. So this dy dx, meaning you are only changing this guy z in x, in terms of x. So x, differentiating x where it is there, it will give you what? It will give you 2x, right? Then y, still the same thing, right? Okay, so I can tell you again to say find now the x dy, all right, of this function. So in this case, you can see x is there, so meaning you need to make x the subject of the formula. So you say z is equal to what? X squared y. Then from there, then you make x the subject of the formula. All right, so z over y, then you square. All right, so they are both in the what? In the root. So we have z to the power 1 over 2, and also y to the power what? 1 over 2, like that. Then you can take z to the power 1 over 2, then y to the power negative 1 over 2. Then that's when you now you find the dx, then dy. So the only change in y, you go and differentiate where y is. Then that will be simple for you. Hope that is clear, and hope that was help. That's what you did in the last meeting we had with our doc Ahmad. So thank you very much for watching and also following the lesson. See you in the next session as well.